Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we are absolutely thrilled to have John Kleinberg here. This is the first public lecture at Microsoft Research New England, and so we chose our favorite speaker. And it's actually probably good that it's raining, or else there would be too many people in the room. So, so we arranged the rain so that we wouldn't go over the capacity of the room. And John is going to be telling us about his work with a few other people, looks like all of Cornell, on computational perspectives on social phenomena, status, reputation, and controversy.
Okay. All right. Thanks very much. Let's see. Okay, that seems to be on. I'm not sure if I need the microphone, but... oh, it's taping, right? Yes.
It's not really on to amplify you.
Okay, that sounds good. Good, but everyone can hear back there. Okay, well, thanks for braving the weather, those of you who came from through out of doors to get here. Let me not stand in front of the slides. Okay, great. Well, so thanks very much for the invitation to come speak here, and it's a real pleasure getting the opportunity to visit. What I want to talk about today was some issues at sort of the interface of social and online networks, and both some of the kind of models we're building for what's going on and some of the things we're learning by looking at these systems as they're being used. I mean, to sort of start with some context, and maybe actually some context followed by some sort of backstory of the kind of style of research I'm thinking about here. Let's talk sort of begins at the point where what we could think of as online technological networks begin to merge with social ones. We're reflecting offline, real-world social interactions. And this had a few effects. It, first of all, means that when we think about design problems for these kinds of systems, we have to import things that we know from the social sciences, things from economics and from sociology, from social psychology, anthropology, many areas, into the design of these systems. So when we think about how these systems are designed, they're not only governed by computational limitations, technological limitations, but also by the kind of social feedback effects that happen when you bring together millions of people and have them interact with each other. And that introduces all sorts of new constraints into the design space. Second, and this is sort of maybe the point from which my talk more directly jumps off, there's this principle that really holds across all areas, that science always advances when you can take things that were once invisible and make them visible, make them measurable, right? And so there was sort of this strange paradox that through much of the 20th century, it seemed we knew more about the proteome of yeast or, you know, exploding stars at the edge of the galaxy than we knew about the everyday dynamics of human social groups. And that was kind of ironic because human social groups are something that are part of our everyday experience, whereas these other things were remote and inaccessible to us. And it was really largely about differential powers of measurement. The problem was that social interaction was always this thing that was sort of fleeting, ephemeral, somehow inherently unknowable. And it's really recently that we have these public recorded digital traces of interaction that we're able to start actually making some of these very large-scale predictions, right? And in the process, we see sort of a convergence of areas, right? So we see that the kinds of detailed, complex, nuanced questions that people in the social sciences had asked are beginning to intersect with some of the very large-scale questions that you can ask by computational means. And obviously, both of these styles of research have each things to contribute. And I think what's going to be interesting here in this whole area is to find the places where these lines of research meet, where they converge, where we can actually take some of the complex and nuanced questions and ask them at this scale. I want to do a two-slide digression just at the beginning, just kind of how I got into all of this, what, you know, some backstory. There were a number of interesting questions floating around social networks, you know, in the past 10, 15 years. One that sort of captivated a lot of people's imagination was this idea of the small world phenomenon, the 6 degrees of separation. And I wanted to sort of mention this story in 2 slides, not because it's the subject of my talk, but because it sort of shows an arc that gets closed, beginning with a very creative experiment in social psychology, ending with mathematical models and extremely large-scale data analysis, and the loop closes in a way that sort of feels satisfying, that sort of feels like we've learned something. So it begins with both anecdotal fascination about the idea that we're all a small number of steps apart from each other in society, and also with this very innovative experiment that Stanley Milgram did in 1967. So he wanted to empirically test the idea that there really are short chains of connections through the world's social networks, right? That a friend of a friend of a friend of yours could be anyone at all. And so what he did was, to test this empirically, he had people actually build these paths through the social network of the world, or at least of the United States. He chose a target person, the place where all these paths would end. They lived in Sharon, Massachusetts, about an hour drive south of here, or less. And he chose starter people who he chose at random, some from Boston, most from Nebraska. As he said in his paper, that was sort of far enough away that it seemed like it would be sort of a fair test. They were kind of way out there in the center of the US. And he sent each starter a letter saying, we're trying to test this theory about small connections in society. I'd like you to send this letter to someone you know on a first name basis so as to advance this chain toward this target. The target, here's their name, their address, their occupation. They were a stockbroker who commuted up to Boston and worked in the financial district of Boston, where they went to college, their wife's name, some facts about them. But although you have their address, you can't just mail them the letter directly. Rather, you need to send this to someone you know on a first name basis with the goal of advancing toward the target as fast as possible. Okay, and the now famous conclusion of this experiment was that the median number of steps, not actually the average, but the median number of steps that these letters took as they converged on the target in Boston was 6. Participation rate in this experiment was actually quite high. Roughly 3/4 of the letters actually took the first step. About 1/3 of them made it with a median of 6 steps. And that is what the playwright John Guare then subsequently named in his 1990 play, The 6 Degrees of Separation. Okay, so that was this striking fact about the social network. And this was the object of some amount of mathematical modeling and some interest, but it really sort of caught hold when my colleague Steve Strogatz at Cornell and his then PhD student Duncan Watts, now at Yahoo Research, proposed a very simple mathematical model for what social networks might look like such that they have this small world property, this 6 degrees property. And this was sort of a fun model to play with. It's something I got interested in playing with. You could think of it as a picture of the social network in which everyone lives on a grid. Again, very stylized mathematical model. So everyone lives on this grid, and it basically says everyone knows their next door neighbors in the world, right? So that's sort of a reliable source of friendship, this geographic homophily. And then everyone has these random links, these red links that jump over the surface of the grid. That's what makes the world small, right? So we all have this, you know, even say one very long-range link. And if I superimpose the red and the black links, I get these very short paths. Okay. So it was a fun model to play with. I talked with Duncan and Steve about it. But the thing that sort of intrigued me, and again, this is now going back to some sort of semi-ancient history, 1999, 2000, what intrigued me was the idea that Milgram didn't actually do what, for example, my colleagues at Facebook did, culminating in this thing 2 weeks ago, where you actually just take this 700 million node graph of who's friends with whom, and you run breadth-first search, and you just work out distances. A massive computation, which actually required a very sophisticated algorithmic engineering. But Milgram didn't do this. Why didn't he do this? He didn't have that kind of a data set. He had an experimental budget of $680 to do the entire research, which covered kind of the postage to mail all these people in Nebraska, and not much else. And so he was forced to embark on, fortunately, the much more interesting experiment of asking people to tunnel their way through the social network, right? You can't just run breadth-first search. You need to guess where you should send the letter with the goal of getting this thing to the target as fast as possible. So in effect, he asked people to solve a decentralized routing problem, right? So he didn't actually program them with an algorithm, but he said, you know, make up your own algorithm, right? Think about how you would get this letter, right? So, you know, the person you're trying, you know, and you can think how you would do it. The person you're trying to reach is an amateur rock musician in Portland, Oregon. You know someone in Seattle who knows the music scene. If you get to them, they'll probably be able to get it close by. There are all sorts of clues in the world that helped you reach the target. So if you play around with this model, you can try to formalize that distributed routing problem in this, because in some sense the Watson-Strogatz model fortuitously had exactly the ingredients that you would want to kind of ask this question. It's a network that's partially known because you know the grid, and partially unknown, these red random links. So who knew that your next door neighbor actually knew musicians in Portland? You just didn't know that, right? And so, and you're trying to use, but it's the red part that really produces the short paths. So you're trying to use what you know to infer about what you don't know. And so what turns out is that if you add these links to the grid in a certain probabilistic way, so you say people have faraway links, and the probability that node V links to node W has a probability that decays with distance, 1 over their distance to the alpha power, right? So think of a kind of generalized sort of gravitational law, right? The chance that you know someone distance d away is 1 over d to the alpha. Then, in fact, search, in the sense of Milgram, is most efficient when this exponent is 2. When link probability is 1 over d squared on the grid in 2 dimensions, that's when search is most efficient. Okay, so I wrote this paper in 2000, and at the time it was sort of, what was sort of surprising is it's a very simple model, you can have fun playing with it, and it makes this sort of bizarrely specific prediction that in order for the Milgram experiment to have sort of succeeded, because it isn't just that this is sort of the best among many good options, there's really something sort of critical that happens at this value. And so you sort of felt like, okay, this is a very specific prediction. And I sort of said the kinds of things in the paper that you say when your theoretical model makes more of a specific prediction than you had originally planned for it to make. You know, you said, you know, the real point is just the model, and it's not important whether, you know, the real exponent is really 2 in real life or not, but really the principles about this trade-off between, and it's, who really knew? On the other hand, I thought, you know, in the end, what are the, people would ask, so what is the real exponent? I thought, we don't know. We don't have that data. Even in 2000, even with web crawls and everything, we did not have that data. And I thought, what are the chances we're ever going to get that data? I mean, you'd have to somehow create a service where you convinced tens of millions of people to all sign up, say where they lived, and say who their friends were, right? So, of course, that happened much faster than anyone anticipated. And so it was really in 2005 that social networking sites began providing the kind of data, public data, that really made it possible to ask the question, well, so what really is the exponent? Now, to ask that question, you have to generalize the model. And we, a number of people, me and others, generalize the model in a number of ways. Because, for starters, the population density of the world or the United States, or really any region, is very, very non-uniform. And you can make most things go away from this model. The fact that it's a grid doesn't matter. The fact that it's rectilinear doesn't matter. How many links you have doesn't really matter. But uniform density mattered. And so we need to generalize the model. And maybe the cleanest generalization was actually by David Libin-Nowell and some colleagues at IBM, Ravi Kumar, Jasmine Novak, Prabhakar Raghavan, Andrew Tompkins. And they proposed, rather than stretch and shrink space, let's sort of do it ordinally. Let's do it by ranking. So what we're going to do is say each node V in the system is going to rank all the other nodes by closeness. Okay? So if you live in Manhattan, you're going to rank people very finely because the person next door in your apartment building and 2 doors down. Whereas if you live out in the country, you're going to also rank people, but they're going to be much farther away. And this sort of puts everyone on equal footing. So we'll say that the rank of W with respect to V is the number of nodes that are closer to V than W is. It's just in the sorted order out from V. Okay, so what's the generalization of 1 over d squared? Well, if the population density were uniform, then someone at distance d is on the perimeter of a circle of radius d. A circle has area like d squared, so they would have rank d squared. So therefore, 1 over d squared should be like 1 over rank. And indeed, what they proved was that if you link with probability proportional to 1 over rank, then whatever the density is, you're going to have routing. Okay, so now finally we have something we can actually go and take real data and compare it. And the first paper that actually did this was this paper of Libin-Nowell et al. Using live journal data, which was fairly sparse at that time, about 500,000 people. And if you looked on the east and west coast, where there was enough coverage, enough population density, you discovered that the link probabilities decayed, right? Your chance of knowing someone at rank R fell off like 1 over rank to the 1.05. Remember, the number we're aiming for is 1.0. 5 years later, after the expenditure of enormous amounts of money, people signing up, and hundreds of millions of users, my former PhD student Lars Backstrom with Eric Sun and Cameron Marlowe at Facebook did this on a fairly large piece of the Facebook data and found that probably you're linking to someone at rank R falls off like 1 over rank to the 0.95. So this was surprising, and certainly I was as surprised as anyone else, that these numbers were remarkably close to 1, right? Because here we had this model that, very, very simple model. It made this, coughed up this prediction. And when you actually go and test on these things, you actually find things that are very, very close to 1. And it's all the more surprising for a couple of reasons. The main one being, whatever it is that people are doing on LiveJournal back then, on Facebook now, they're not trying to configure their lives to make the Milgram experiment run as quickly as possible. That's not what they're in this for, right? They're doing all sorts of other things, but they have somehow shaped the network so that that happens, right? It's somehow a case of some kind of convergent evolution where this property came out of the system. And that, therefore, even as it kind of wraps up one kind of story arc beginning with Milgram, it opens up this fascinating open question, which is, what are the selective pressures on the network that are organically driving it toward this exponent of 1? And there are some conjectures, some conjectured processes, because after all, we do things that are somewhat Milgram-like in society, right? So when you're trying to find a job, you talk to people who refer you to other people who refer you to other people. When you're trying to sublet an apartment, you talk to people who refer you to other people. So there are times in your life when you are searching your way through the social network, and as you do that, you tend to remember some of the people you met along the way, which sort of rewires the network in certain ways. And there are arguments that that can actually help drive the network toward this. But exactly why the network is sort of staying on this path is a fascinating and essentially open question. Okay, yeah. How sharp is the...
The 2 or 1 doesn't exist.
Oh, you mean how good is the fit? Yeah, I don't have plots here. So this gets into the sort of technology of how do you fit power laws to data. So certainly when you look, so let me just say something qualitative, which is that if you look at the plots, through most of the Bayes distribution, it's a fairly strong fit. Here especially, so there's it really looks more like sort of 1 over rank plus 100 to the 0.95, because there's a drooping at the head of the distribution. But once it gets in the Bayes distribution, it's remarkably straight. Yeah? Oh, this is actual geographic distance. This is miles. Yeah. I mean, here they had zip codes, so it was a proxy for distance because you would take the kind of zip code location from the USPS database. Here, it's whatever. Yeah, as finely as they can resolve geography. And of course, geography is not everything here, right? So I'm hiding in these references here. There are many other forms of distance you can use, and other notions of social distance, like take some hierarchy on characteristics of people, and then look at distance in that space. And one can have versions of that result there also. Yeah.
It's clear that maybe that you don't want the exponent to be maybe too large because then you won't have a lot of neighbors far away. But why is it bad for search if the exponent is too small? You have too many neighbors, you don't know which one to choose? Or?
Yeah, so if the exponent is too small, and even if I normalize it so you have fixed degree, so you always have a fixed number of neighbors. Yeah, so if the exponent is too large, you can't take long jumps. The exponent is too small, that's the more subtle one. I guess the point is, say you're trying to find a stockbroker who lives in Boston. The reason you send the letter to Boston is because there better be a greater density of links among Bostonians than there is among the population at large. And that requires the exponent to be at least sufficiently large, right? So the reason you sent the letter to Seattle to reach Portland is, so essentially you need a distribution of distances so that however far you are from the target, you always can reliably essentially have your distance. And that's essentially, if you work out what is the exponent where you can always reliably have your distance, there's actually only one that does that. And that's essentially the whole analysis. Yeah. Other questions about this? And again, this is sort of just a snapshot of this kind of picture of, again, starting with Milgram and then going on to these things. Yes.
So when you mentioned you sent it sort of to Seattle to get maybe somewhere to Portland, and so what you also seem to be implying that you actually sent it to area which is where the density of population is higher. So is there some?
You're more likely to send it there because you're more likely to know someone in Seattle than in Portland has a greater population. So it isn't necessarily your agency that causes that to happen. It's simply that if I'm allocating links at random,
But how is it you said that the density is constant was sort of important. So, but is there some heuristic?
It's no longer important once you do rank-based. Then density.
Oh, not at all.
Right. Then density doesn't matter at all. Yeah.
So it's true for all graphs, is that a theorem?
True for all point densities in the plane, right? So I put down points under any density of the plane, under mild assumptions, but pretty mild. Okay, so after we started, so it was really 2005 we started, and because 2005 was when we began seeing data like this from social media sites. Of course, we even then didn't really anticipate how rich it was going to become. But at that point, we sort of sat down, and a number of the Cornell, especially like Dan Huntlarker and me in computer science, Michael Macy in sociology, and Michael especially, as a sociologist, was sort of especially passionate about this point that there's really a chance to take some of this data and try addressing in new ways some of the sort of classical puzzles of 20th century sociology, right? So puzzles like peer influence, right? The probability that you engage in some new activity as a function of the number of friends that you have who are engaged in that activity. Questions like what's the basis for homophily in social networks? Namely, why are you similar to your friends, right? Are you similar to your friends, say, in interests, beliefs, and opinions because they influence you and cause you to believe the way they do? Or is it because you don't necessarily change your mind, but you seek out others who are like you in the first place, right? So those kinds of questions, which have, again been long a challenge. Similarly, how do you evaluate other people, right? How do positive and negative interactions with people mix when you form a social network, right? Not just the friendships, but also the rivalries and the antagonisms. And on all of these, there's been actually now a growing body of work that has tried to use online social media data to pose the question in a way that can be answered with those data sets. There's also been increasing interaction with sociologists, social psychologists, and other people from the social sciences to try shaping the questions in ways that really make sense. And I think that's another important point in all of this, that in 2005, when I first started giving talks about the potential of this data, I think it always takes a while to sort of calibrate the message of one's talk. I would show up and social scientists would hear me say, we have, gigabytes and terabytes of this social data, and it's enormous, and we will bury you, right? And that really wasn't what was intended, It was really a case of, we have a certain style of doing research. It has some strengths. You can see these patterns that are very, very subtle that occur at large scales. And it has some weaknesses, right? We haven't gone and figured out exactly why all these links are there or who these people are. And we, therefore, on our own, can't ask the same kind of complex, nuanced questions. And so it was really a case of, how do we find, as I said, the point where these lines of research converge? And that's what's been going on through all of these questions and others. What I wanted to do is sort of zoom in on this last question. How people evaluate each other, how positive and negative interactions mix in the social network. And sort of talk about some of the stuff we've been doing there, some of the phenomena we've observed, and then also some mathematical models that we've built. Okay, so there are lots of actual situations where one person expresses an opinion about another, or maybe content that they're closely associated with. And I want to look for domains in which, right, so on Facebook you can like something. There's not as direct a mechanism for disliking something. But there are many domains where you can actually express likes and dislikes. And I want to look for data where you can actually express the sign of your feelings, right? Plus or minus, and then ask how these pluses and minuses deal with each other. Now, pluses and minuses mean different things in different contexts, right? So on a product rating site, for example, it might be a trust network. I trust you or I distrust you. On blogs, for example, political discussion, it could be I agree with you or I disagree with you. I didn't have an icon for the blogosphere, so I took this nice picture that Lotta Adamich and Natalie Glantz did of the hopelessly polarized political blogosphere into two camps, red and blue, and that can be my icon for that. Wikipedia has lots of evaluation going on in it. So in fact, one that we'll look at is that when you want to become a Wikipedia admin, right? So Wikipedia has an army of order of a couple thousand volunteer system administrators who have the ability to lock down articles, resolve disputes, and generally take sysadmin kind of actions. Of course, with that kind of power, they have to actually vet you. They have to make sure it's safe to give you this power. And so there's in fact a kind of full tenure and promotion process that you go through when you want to become a Wikipedia admin. You submit essentially your Wikipedia CV. You say, here are all the good deeds I've done on Wikipedia. At that point, you typically have logged roughly 10,000 edits or more on Wikipedia. And there's then a community discussion, a public discussion, and a public vote on whether to admit you into the community. And that too has positive and negative signs attached to it. When someone votes against admitting you into the community, that's a vote that's public, negative, and consequential, right? Because you really wanted to be admitted. So it's another case where we have positives and negatives. And finally, if we think about a site like Amazon, we could talk about reviews you find helpful or non-helpful, and again, we have positives and negatives being traded off. I guess you'll find actually that if you think back over various of my metaphors, I tend to often sort of reach for analogies to the academic domain, right? Tenure and promotion, citations to papers, and so forth. That's probably because I'm trapped in this sort of academic mindset. But it is the case that there are many natural analogs to offline domains. And if I have time at the end, I'll talk a little bit about some work that my students, Sigal Oren and I have been doing, thinking about what some of this notion of evaluation might mean in the context of the sociology of science and academic credit in general. Okay, so that's the plan, how positives and negatives interact. Let me grab this back so I can keep track of what time it is. Okay, so let's do that. Okay, so here's the plan. One problem is that when I give you the power to say trust or distrust, vote yes or no, helpful, not helpful, really, you might be trying to express many, a number of possible things, right? And when someone says, what do you think of this person? You'd say, well, my actual opinion is very complex and nuanced. They say, no, just press the button, like or dislike, right? So it's been bundled into this very complicated thing. This complicated thing has been bundled into this one bit. And it's sort of up to these models that we build to try pulling back out what it really means. And so we're going to try mapping this onto basic social science theories, right? So one is a theory of structural balance, which basically says pluses and minuses behave like friend-enemy relations. Another is a theory of status, which is that plus-minus relations in other contexts might behave like, deference or lack of deference, as in I look up to you, I look down on you. Okay, so and we'll look at the extent to which each of these is reflected in data. So we'll look at balance versus status, and we'll look, if I have time, although I might bypass this, how people evaluate opinions also. Okay, and then finally, as promised, I'll talk a bit about what this means in the offline world, thinking about evaluation in the context of scientific credit and the perennial question of whether the right things are getting enough scientific credit. Okay, that's the plan. So let's talk about structural balance, which is the first of these theories. It says that maybe things look like friend-enemy relations. So if we think about friend-enemy relations, this goes back to work of Fritz Heider in the 1940s, a social psychologist, and then kind of hybrid graph theorist psychologist team of Cartwright and Harari in the 50s who tried to formalize these ideas in the language of graph theory. And it begins actually from some very old proverbs, which you can find written in a number of different languages. And they say things like, the friend of my friend is my friend, the enemy of my friend is my enemy. I won't read through them all for you, but you get the idea. Actually, I don't want to dwell too much on the numerology of Proverbs, but let me point out a couple things here. So it's, the blank of my blank is my blank, and in each of those arguments you can put friend or enemy. So that's two to the third possible proverbs you could write. That's 8. But some of those are kind of crazy. Like, the friend of my friend is my enemy. That'd be like nuts, right? So I wrote the 4 that make sense, right? So 4 of the 8 make sense. And the ones that make sense are the ones where the word friend occurs an odd number of times. Okay? Now, none of that is actually a coincidence. And the reason it's not a coincidence is if you think about this as Cartwright and Harari did, not in just this big bunch of words, but in the language of graphs. Okay? So these are all statements about triples of people, 3 people at a time. And it's about how you can sign triangles, right? So if I have a triangle on A, B, and C, then there are 8 ways of signing it if I care about the labeling, but up to symmetry, there are only 4 distinct ways of signing it. 3 pluses, 2 pluses, 1 plus, or 0 pluses, and then everything else is just a kind of rotation of those. And what Heider proposed, or this is in Cartwright and Harari's language, that certain of these things are psychologically and cognitively more plausible than others. Okay? And so we'll call the plausible ones balanced. So 3 mutual friends, for example, is balanced. It obeys the logic of these proverbs. 2 friends with a mutual enemy is also balanced. I mean, it's too bad that A and B don't like C, but there's nothing psychologically implausible about it, right? They're just enemies. Things get more tricky when you look at these other kinds of triangles, right? So one of the basic arguments of balance theory is that this triangle is not balanced, right? So A is friends with 2 people, B and C are enemies, right? Maybe it's that, B and C used to be going out, now they've broken up, and so now A has this problem that they're friends with both of them, but when they talk to B, all B does is complains about C, and when they talk to C, all C does is complain about B. And so something has to give, right? Either A has to get them to reconcile, or A will end up siding with one against the other. It's out of balance. There's some potential energy that needs to be resolved. Balance theory is somewhat divided on this last one, right? So the sort of mainstream of balance theory says this too is not balanced, 3 mutual enemies. It depends on the context, right? So what's the argument for why it's not balanced? Well, if you think back, for example, to say the contentious end of the 2008 Democratic primary, because you often think about this in political or international relations situations, there were 3 people who arguably mutually really did not get along, right? Obama, Clinton, and McCain. Right? They were all mutually rivalrous, say, in May of 2008, but there was a sense that that was not sustainable, right? Maybe there would really be a 3-person general election. More likely, the 2 who disagreed the least were going to team up against the 3rd, which is, of course, what happened. Right? Of course, there are other parts of balance theory which say this is not totally unbalanced, but
It's one person who hates everybody, and now the rest of the world is forced to be friends.
if you believe, well, let me get that on the next slide, actually, yeah. I mean, there is this, even that happens, right? I mean, certainly there is the political technique of uniting a divided legislature against a common enemy, which is essentially what that is, right? Right. We've temporarily put aside our differences for the greater good is a statement about balance. yeah, let me actually make that point on the next slide. This was actually the basic theorem that Frank Harari proved in the 1950s, which is, and this is actually I would say a surprising theorem. You could ask, take a complete graph. So small set of people, everyone knows everyone. Political situation, a bunch of countries, whatever. Say that every triangle is balanced. What do I know about the resulting graph? It turns out you know an awful lot about the resulting graph. It turns out if all the triangles in a signed complete graph are balanced, then in fact, the only way that can happen is if the nodes are partitioned into two rival camps, so that inside each set, they're all friends, and in between, they're all enemies. Okay? Clearly, that is balanced, because every triangle has either all three ends on one side or two here and one there. The non-trivial part is that those are the only balanced configurations. Okay? All right. So this is actually often pointed to as a very nice example, sort of early in the mathematical social sciences, of local implies global. Right? I made an assumption about three people at a time, and I got some statement about the existence of factions, which we see borne out in many contexts, to go back to my newly nominated icon for the political blogosphere. Okay, so actually, one question, and this is more of a mathematical nature, which before I wrap up the discussion of balance theory, I just wanted to kind of lead into. There was this open question, really even from back then, of describe a plausible dynamics that leads to this global structure. Right, so I told you this story, and the story had a big dynamic component. You know, A was friends with B and C, but something had to give. There's all this energy, and you know, here maybe two would team up. That all sounds great, but as with so many stories in the mathematical social sciences, it's a little slippery. What they end up describing is the static equilibrium outcome, and they didn't quite tell you how that story got you to the equilibrium. Right? What actually drives a disordered system where things are out of balance into a balanced system? And that was actually a puzzle for a long time, and it was really cast into sharp relief by three physicists here at BU, Antal, Krapivsky, and Redner, who explored a whole bunch of dynamics that might guide a system toward that. Their rules were actually local, and the way they worked was to imagine structural balance as a kind of, the search for structural balance as a kind of local search. So it says, here are A and B. They're trying to decide whether to be friends or enemies, so they're going to look at their relation to third parties. All right? And when they look at their relation to third parties, one way to summarize the principle of structural balance is to say that to the extent that we agree on how we feel about people, we should be friends. And to the extent that we disagree on how we feel about people, we should be enemies. And that kind of summarizes all four triangles. Right, so A and B might say, all right, we agree on how we feel about W, X, and Y. We agree about Y. We both hate them, but we agree. And Z, we disagree on. Okay? Therefore, by a vote of 3-to-1, we should be friends. That's very simple dynamics that would try to resolve, and it actually in a sense is energy minimizing. If you view the triangles as having energy when they're out of balance, then picking plus here is the energy minimizing step because it only creates one unbalanced triangle instead of three. Okay? So it's actually in a way like a sort of physical spin system because there are pluses and minuses. Although note that the spins here are on the edges, right? Normally when I talk about spin systems, the spins are on the nodes. They spin positive or negative or up or down. Here they're on the edges, which my physics friends tells me means that it should be called a gauge theory, for whatever that's worth. But the point is, the system tries to sort its way out. It does local search. And the difficulty with this, actually, and again, Antal, Krapivsky, and Redner really explored this very nicely. We did a little stuff with this in 2009. The system gets trapped in numerous local optima on its way toward balance. It does not find structural balance. Okay. At the same time, there were three physicists in Poland, Kulikowski was sort of the driving force in this, who proposed a totally different view of this, a continuous dynamics that drives things toward balance. And this turned out to lead to actually quite a satisfying idea for how you might actually drive a system toward balance dynamically over time. And it basically just took this idea and made it continuous. It said, let's think about nodes I and J and whether they're friends or enemies. But let's encode how they feel about each other with a real number, xij. Right? So it's not just plus or minus, but it's a signed real number. So very positive means they're very friendly, very negative means they're very unfriendly, and so forth. Now let's encode this idea that when you agree how you feel about people, that makes you more friendly. And when you disagree on how you feel about people, that makes you less friendly. So what I could do is say, and this will be my only differential equation in the talk, so for those of you who don't like differential equations, don't worry. But I could say, what's the rate of change of how we feel about each other? Well, for every third party, let's look at the product of how we feel about them. xik times xkj says, if these have the same sign, it pushes our friendship up. And when these have opposite signs, it pushes our friendship down. So very, very simple differential equation that pushes this in the direction of whether we tend to agree more or disagree more on how we feel about people. Okay? And the surprise was, and this was some work that I did with Bobby Kleinberg, Steve Strogatz, and Steve's then student Seth Marvel, was that if we start with generic initial conditions, so essentially say a random initial start, and if we normalize the system so the numbers don't grow unboundedly, then actually within finite time it converges to structural balance. It actually converges to a state where how two people feel about each other can be encoded by saying there's a number on node I, yi, and a number on node j, and how they feel about each other is equal to the product. Okay? So essentially it takes this very complicated graph with people feeling plus and minus, and it squashes it down to essentially a one-dimensional political spectrum. Right? Everyone stakes out a position on this political spectrum, y sub I. And when two people on the political spectrum have to decide if they're friends or enemies, they just multiply their values. So two negatives are friends, two positives are friends, and if you're on opposite sides of 0, you're enemies. Okay? So, and in fact, we can say what these numbers are. It's essentially an eigenvector of the initial matrix. And so it leads to a number of interesting questions. If we take this as a plausible dynamics for balance, how we reason about things like convergence speed or how different initial conditions lead to different kinds of outcomes. Okay, yeah.
It's related to the process where instead of choosing the edge that makes the most triangles balance, you would choose it kind of probabilistically based on
Yeah,
this.
so, right, so Anton Kaprisky and Redner again looked at some probabilistic rules. So that would be sort of a metropolis algorithm that tries to get out of local minima. I don't see a direct connection to this. This somehow manages to rebuild the landscape so it just glides straight down. We actually don't quite know what this is related to. I mean, it's not that hard to prove this, and the eigenvector is suggestive, but it's not power iteration, right? Because if you think about power iteration iterates through numbers on the nodes. You've got these numbers on the nodes, they're not quite an eigenvector, they're not quite an eigenvector, and over time they become an eigenvector. This is not doing that. This is iterating through numbers on the edges. It's got numbers on the edges that are a matrix, and it's not quite rank 1, and it's not quite rank 1, and it kind of finally gets squashed down until it's just a product. So it arrives at the eigenvector through some other means, which surely at some deeper level is going to be related to eigenvector iterations, but there's interesting open questions as to exactly here. Other questions about this? Yeah. Yeah, so what's funny is it's only controlled by the eigenvalue of the matrix. So yeah, so because I don't tend to, I mean, Steve's more comfortable writing papers where he says things like blows up in finite time, whereas I don't tend to write papers that say that. But that's what this does. So this in a time that depends, so if we didn't normalize, these values would all diverge to infinity at a time that's equal to the largest, something based on the largest eigenvector of this matrix, eigenvalue of this matrix. If we normalize, then at that time we now basically have arrived at those numbers. Yeah, so it's a strange differential equation that sort of diverges. Right, so if you think about like the differential equation dx dt equals x squared, that's going to be something that basically blows up within a finite amount of time. But yeah, it's a weird differential equation in that sense. Other questions?
In the discrete case, the local optimum, is it a cycle? So it's just cycling through things, or does it get to a state where
Where nothing changes, yeah. So for example, 3 large rival camps would be a local minimum here, but it's not balanced. Because no one person is going to want to unilaterally sort of bust out of that situation, but it's far from balanced. Yeah. Good. Other questions? So, okay. Let's go to data and ask, so what does this actually all, kind of look like? So in order to look at this was all about balance. A totally different interpretation, right? So when we're looking online at social media, links are directed. They tend to be created from one person to another one, at least when we're talking about evaluation. I evaluate you. We may not know what you think of me. So a proposal starting in sociology and actually explored a lot in the web research community by Guha et al. Was that maybe we should think about plus and minus as having a different meaning. That A linking positively to B means that A has lower status than B. A looks up to B. And A linking negatively to B means A has higher status and they look down on B. Okay? Now, what's interesting here is that these predictions make different, two theories, balance and status, right? So one is a theory of bipartite splits, another is a theory of basically acyclicity, that there's a pecking order in the world and you either look up to someone or you look down on someone. They make fundamentally different predictions, right? So here's an example where they make different predictions. So suppose we know that A is negative toward X and X is negative toward B. Then balance says, well, A and B have a mutual enemy, they should be friends. But status says A looks down on X and X looks down on B, so A should really look down on B, And we actually find in most of these online systems that we looked at, ePinions, Wikipedia, Slashdot has features like this also where you have not just friends but foes. We find that minus is much more prevalent, in fact, that it behaves as though people are following the predictions of status. Similarly, and even more surprising predictions get borne out by status. So for example, if we know in these systems that B is positive toward X and X is positive toward A, balance finds this very easy. I mean, it's, after all, they're friends and they're friends, so they should all be friends. But if we really ask, how does A evaluate B, status would say something different. B looks up to X looks up to A, maybe A should look down on B. And if you find that strange, then, to invoke yet another academic analogy, imagine that you're listening in on some hiring discussion where B says that, you know, they should hire X because X is a real superstar, and X says they should hire A because A is a real superstar. And then you ask A what they think of B. You know, A would be polite, of course, you know, but maybe A would actually look down on B. I mean, maybe A really, right? So status really would make a prediction like that. And again, we see in all these data sets that this minus prediction is actually overrepresented in the data, right? I mean, we see lots of pluses because there are pluses everywhere, but more than you would otherwise predict against the baseline. Now, I should mention, it's more subtle than this. And in fact, different theories seem appropriate in different parts of the network. So in particular, these networks are largely non-reciprocal. When A evaluates B, we tend not to see B's evaluation of A. But if we focus on the parts of the network where the links go both ways, we see balance applying much more strongly. Right? So it says that actually people are using different meanings for these links when, you know, they're in different parts of the network, right? So mutual relationships that go both ways, tend to have more that's based on things like balance. And it also, I think, has this interesting design implication, back to this point that we're trying to unpack the different meanings people gave to their links, that really balance and status are partly encoding some kind of difference between I agree with you and I respect you, right? Balance is a theory of agreement. Status is a theory of deference. And to the extent we could actually make those two different dimensions, it creates interesting kinds of design questions. Yeah?
Example where this like plus minus prediction gets borne out?
An example where?
Just like anywhere.
I mean, like Wikipedia voting. If I know that B voted positively on X and X voted positively on A, that creates a kind of depressed probability of A voting positively on B relative to the baseline. Would be an example. Same with trust networks and opinions. So that's not saying I know A is going to be negative toward B, but it says I have some baseline. I have some default baseline probability, and it depresses it relative to that baseline.
These kind of things you would see kind of naturally a hierarchy of a shrinking pyramid where both class links go up or something?
Yeah, so there are interesting open questions here, which we don't fully understand, where locally we see a lot of evidence of status. You would expect, therefore, you could extract some kind of giant acyclic network that all points in the direction of higher status. And it is true that you see larger acyclic subgraphs than you would predict by chance, which is consistent, but not as large as you might want. And so it says somehow what's happening locally is not preserved all the way up to the global level. And there are actually interesting questions about sort of approximate transference, right? So if I know that approximately, say, status holds at a local level, what can I say globally? Is an interesting question in a lot of respects. Yeah? Email. I mean, it'd be a good question to look at measure. So what would the measure of status be? I mean, whether you get a reply, yeah, right. Interesting question. No, and it's a nice question to ask why, whether you would see those sorts of things. I mean, it certainly, balance would not be a plausible thing for email probably, but yeah, but you could expect that. There's been a little work by Bernardo Huberman and his group on sort of speed of response in email and what the, and actually we've done a little work on reciprocity on Twitter, which has some of that, and you do see effects of status and whether someone is going to sort of reciprocally follow you, for example. Yeah. Yeah, good question. Okay, so once we understood that status was going on here, we thought, okay, so status is this subtle thing. So we did a couple things. There was some machine learning we did, which I won't get into the details of, but instead I wanted to sort of discuss one subtlety that came out of this. So here's what we looked at. If status is really important, well, there are things that are markers of status that are intrinsic to you, right? So for example, I mentioned that when you go up for promotion on Wikipedia, you've often logged 10,000 or more edits on the system. So I could look at your edit count as an overt sort of marker for status. It's not exactly your status, but it's a marker of your achievement level. And we said, if a voter of achievement level X votes on a candidate of achievement level Y, what's the chance they vote positively as a function of the difference in these achievement levels, in these edit counts? You would expect that to a greater degree that the voter outranks the candidate, the probability of voting positively should go down. Okay? So we made that plot. You have enough data on Wikipedia to make that plot, and there's that plot. Okay, so here's the probability of a positive vote. And on all these systems, the probability of a positive link is about 80%. Because after all, negative links are socially and cognitively more costly, I mean negative evaluations. And so you see positive links in general, which is why we need baselines for all of this. Okay, 80%. And so here's the difference in the edit counts of the voter minus the candidate. So it should go down. And, you know, so this was some stuff that Yuri Leskovich, Dan Huttenlocher, and I looked at as part of the work we were doing there. And we were happy to see that indeed it went down. And Dan, Yuri, and I, when we look at this stuff, sometimes we're a little slow on the uptake. So we, you know, for the first month or so, we just noticed it went down. After about a month or so, we noticed the much more interesting feature of this plot, this local minimum right around 0. And we did it for other measures of achievement. So like barn stars, which are like these badges of merit you can get on Wikipedia. And in fact, there too, you found this downward trend. If the voter has more barn stars, which are their badges of merit, than the candidate, it goes down. But there's again that dip right around 0. And so it's an interesting question what this means. If we want to interpret it literally, right, what does it literally say? It says people are especially negative on others whose achievement level is the same as theirs. Right when someone is equal to you, you're especially harsh, and then there's this rebound as you get more. And we're starting to sort out, especially with some nice work that Yuri's student Ashton Anderson at Stanford is doing, starting to sort out some of the underlying causes of why that might be happening. I'm happy to get into some of that. There's some interesting stories there. But what I want to do is jump to some of this in the offline world, just to kind of add one more twist to some of these questions about status and evaluation. Let me skip those. Okay. So somehow throughout this, I've been sort of talking about notions of status and bringing up these academic analogies. And so I wanted to actually talk about some work that Sigal, Loren, and I have been doing on this question about scientific credit. And what do notions of status and evaluation tell us if we try to build models of how credit is allocated in scientific communities? And so obviously, scientific communities have lots of explicit notions of credit, right? There's acceptances of papers, there's funding of grant proposals, there's who gets hired, and so forth. And also, I guess I would argue that not only that, but there really is some amount of planning that goes into all of this, right? Yes, there's a lot of decentralization across different institutions, but right, there really are program committees that sit down and say, what kind of work do we want to accept? There are funding agencies that decide what kind of research do we want to prioritize. And, you know, in general, research communities, much more so than other parts of the, you know, economy or world, sit down and actually articulate their priorities. They say, we value this, we don't value that. And those are signals that students, postdocs, young faculty, old faculty, researchers, and everyone respond to. So there is sort of a planned economy kind of thing going on. And so what kind of motivated me really was some very interesting thinking going on in the CS theory community about this question of how scientific credit was allocated. And there was this nice thing that got written, which got posted on Scott Aronson's blog a couple years ago, about, you know, what were essentially sort of pathologies in how credit is being allocated, and the interesting question of what to do about them, right? And right, so in particular, this sort of distinction where, you know, papers that seem to be sort of technically very difficult were getting accepted, seemingly at the expense of papers that were less technically difficult, conceptually, you know, more novel. And part of the question here was, what's going on? You know, there's what should we do about it, but there's also why is it happening, right? So in doing this, there actually were these sort of two pathologies, both of which have some amount of history in the sociology of science. And so the question was, how can we think about this? So here, in a nutshell, were the two pathologies. The one from here that ended up on Scott's blog, although it had all these signatories, was that certain research questions receive what you call an unfair amount of credit, right? So progress on some questions is very heavily rewarded, even though the community somehow, they agree that others are equally important, but they somehow can't seem to get their act together to actually reward those by accepting them to conferences or funding them, right? And often this seems to be wrapped up with technical difficulty. A second one, which is sort of the dual, and actually in a sense I'll make precise, it's kind of the dual problem, is that not only do certain problems or certain questions receive unfair credit, certain people seem to receive an unfair amount of credit. And this is actually probably one of the most famous observations in the sociology of science. It's Robert Merton's Matthew effect from 1968, that when there's an independent or joint discovery, the more famous researcher tends to get more of the credit, right? This is called the Matthew effect because Robert Merton was invoking the book of Matthew from the New Testament of the Bible, where there's a sentence that basically says, they that have shall get more, and they that don't have very much shall lose even that. Okay, that's the Matthew effect. Okay, so the interesting question here is that maybe this is just a story about how humans have these inherent cognitive biases, and this recurringly leads to unfairness. But the question is there something else going on here, right? Is there something sort of, is there a more robust aspect to this, which is why it seems to keep popping up, right? So because when you have this cognitive bias and it just keeps popping up, you suspect there's something that keeps putting it back into the foreground. What could that be? So it turns out there's a bunch of work that's thought about this. And this is work scattered across the philosophy of science, the economics of science. People like Ken Arrow have worked on it. I guess that's actually an example of the Matthew effect, because lots of people have worked on it, but I mentioned Ken Arrow. Theories of research and development. Lots of areas have actually thought about this. There's a quote by Pierre Bourdieu, a philosopher of science who actually worked a lot also on social capital, which actually kind of summarizes how scientific creates incentives in a nice way. He talks about researchers' motivations are organized by reference to conscious or unconscious anticipation of the average chances of profit. They concentrate on those problems regarded as the most important ones, but the intense competition which is then triggered off likely bring about a fall in the average rates of profit, and hence the departure of a fraction of some researchers toward other objects which are less prestigious, but around which the competition is less intense, so they offer profits that are at least as great. Which, for a French philosopher of science, is a remarkably apt description of essentially load shedding in a parallel system, right? You've got this hotspot, everyone is working on this thing, and because therefore your chance of actually being the one who gets the credit for it becomes so low, you move off in search of other things. Less important problems where there's less competition. That's what I say. So, I mean, this was concrete enough you felt like there's something you could actually make almost mathematical, and that actually started with work of Philip Kitcher, who was another philosopher of science, who introduced a very, very simple game theoretic model into this, because there's something inherently game theoretic about this, right? We have people choosing strategies, what to work on, and they're getting payoffs, which is whether they receive credit for having solved the problem. So Sigal Loren, my student, and I started by adapting Philip Kitcher's model. So I wanted to briefly tell you his model, tell you sort of what happens in it, and then I'll wrap up. Okay, so again, it's adapted. He was sort of more motivated by the natural sciences. We wanted to have something that was sort of more concretely looked like theoretical computer science or discrete math or math in general. So a very, very simple picture of a community trying to solve research problems. So on the left here, I have researchers, and on the right, I have projects. Okay, and so think of these each as an open problem, and there's all sorts of things we could talk about: collaboration, results building on each other. I'm going to skip all that because I want a very simple model. And in my simple model, each of these is an open problem, and you either solve it or you don't. Open problems have two properties. They have an importance, which I'll call the weight. That's just how, and let's again assume, because the results actually will be starker if we make this assumption, everyone agrees on how important they are. There's not disagreement on how important this problem is. Okay, so it has a weight Wx, and it has a hardness, a difficulty F sub x, which is your chance of failing if you try working on it. Okay, so now what's going to happen? So everyone chooses something, and kj will denote the number of players who choose project j. So kx is 2, ky and kz are 1. Okay, so there are two things going on, as in anything with a game theoretic structure, right? So this is a game theoretic problem. There are players, they choose strategies, they get payoffs. It's a very simple game theoretic model. We could ask about society's benefit and players' benefits. So society's benefit is simply the expected importance of everything that gets solved. Well, what's that? So the sum over all projects j of the importance of that project times the chance it gets solved. What's the chance it gets solved? Well, kj people, one of them has to not fail, I guess, right? So it's the complement of the event where they all fail. That's this. So that's the expected payoff to society. A researcher evaluates things differently. Their benefit is, well, if they're on project j, then the chance it gets solved is this wj times the chance, its importance times the chance it gets solved. But by symmetry, someone will get the credit. Someone will have done it first. And so it's divided by kj. Right? And this is Pierre Bourdieu's intense competition, which might scare people away from this problem. Okay. And so following Philip Kitcher's suggestion, let's think about a Nash equilibrium of this research community. Right? A situation where people have chosen, and even given the choices, no one has an incentive to choose some other problem. Okay. Let me give you a worked example, because the worked example will show something interesting. Okay, so a very simple research community. I could build bigger examples, but bear with me while I build a little 2x2 example with 2 researchers and 2 problems. One problem is more important and easier. So it has a weight of 1, it has a hardness of a half. The other problem is less important by a little bit, 9/10 importance and a hardness of 2/3. Your chance of failing is 2/3. So on the left is the unique Nash equilibrium of this system, because both people are trying to solve the more important, easier problem, and each player is getting a payoff of, well, it's going to be solved with probably 3/4, and they are equally likely to get the credit, so 3/8. And if you were to be scared off by the competition and you went here, Well, you'd only get 1/3 times 9/10, which is 3/10. Not worth switching. That's the unique Nash equilibrium. Okay, so this is the only situation where no one wants to change. But it's not socially optimal. Socially optimal would be if they worked on different problems, because then this would contribute an expected value of 1/2, and this would contribute an expected value of 3/10, and that's bigger. Okay, fine. I can dream up lots of games where the Nash equilibrium is not socially optimum. This is yet another one. You know, it's a little unfortunate that everyone's trying to cherry pick this problem instead of doing what's good for society, but not surprising. Okay, but what's different here is that, in a sense, the research community, as we said, it's sort of a planned economy. It gets to build its own rules. Suppose you were in charge of the world, and you could change certain things here. What would you do differently? Well, you could do some things differently. For example, you could decide that although we all agree that this problem Y, is less important, we're going to pretend that it's more important. If you solve this problem, you'll get large amount of credit, let's say 6/5, not 9/10. Okay? This now defines a new game. Now remember, the social welfare is still computed using the true importance, because the social welfare is going to be evaluated by the outside world, right? So the National Science Foundation will go look at this community and say, how are they doing? Are they solving important problems? They're going to use the real weights. Right? But you don't have to use the real weights. You can use these other weights. And so if we do this, suddenly the unique Nash equilibrium actually becomes socially optimal. Right? So we've induced the correct effort for the outside world by doing this. And so it's making this point that to optimize collective productivity, sometimes the community needs to invent this artificial currency.
By deciding which problem to solve.
You are.
But
social welfare, and the outside world, National Science Foundation, whoever, is evaluating using the real weights. But we've decided that your credit as a researcher will be 6/5 if you solve this. We're all going to agree on that.
Make the program easier.
That's true. As I said, if you could change the things under your control, yes, that would be.
So you show it or something that it's always in that direction of adding more credit to the problems that are harder? Or?
It turns out, so I'll get to that. It's hard to characterize exactly, but if you build sort of simply parameterized classes, that's the direction things tend to go in. There are certain versions of this that actually become computationally hard to work out the optimal weights, and then it's hard to say much structure. Yeah.
So essentially what you're saying here is that it's a good thing that not everybody has good taste.
Well, the community is agreeing on what its taste is, right? The community has invented a,
But that means it's bad taste. I mean,
yeah, the community has bad taste, but the community agrees on its bad taste. Yeah, in this example, it is good for the world that the community has bad taste. That is what this is saying. I'm not saying if that's a good thing or a bad thing. I'm simply saying that that's what's happening in this model. Yes.
So what is a pure national escapism?
There is, because it's a congestion game, which I'll get to. Yeah. I won't have much time to go into the details of this, but we could talk offline. But so you've created this sort of artificial currency system. I want to mention another thing. I said the Matthew effect was sort of dual to this. There's another thing we could actually rig. We can't make the problems easier, which would have been a nice idea. We can differentially allocate credit to the researchers. Here's something else I could say. I could say, although A and B are identical, A is, went to has a PhD from a higher ranked institution, or they're taller, or who knows what. They're going to get more, if they both solve this thing, A is going to get more credit. I'm just going to announce that. So if both players succeed on the same project, then A will receive credit with probably C over C plus 1, and B will receive credit with probably 1 over C plus 1. Here too, I can actually now achieve social optimality. If I raise A's share high enough, B won't bother trying to compete on problem X, because they're going to get a small share of the credit anyway, so they're going to go work here, right? And this is a kind of Matthew effect. I haven't built fame into the system, but it broke the symmetry, right? Here too, something really bad is happening, although it's optimizing social welfare. What's bad is that, let me put it this way, by marginalizing certain people unfairly, you are forcing them to pursue riskier courses of action that ultimately you're benefiting society as a whole. It's something sort of inherently unfortunate that, again, is coming out of the model, right? So what's the argument here? The argument is, in these simple examples, there's a kind of robustness to this phenomenon, right? It's bad, it's unfair, it's the result of human cognitive biases, but when it happens, it's actually doing something that's optimizing output, and therefore maybe is arguably a little hard to make go away. There are some general theorems you can say here, and this gets to Boaz's question. So first, there are existence. So there's always a pure Nash equilibrium. In fact, for all sets of instances, there's always a reweighting of the project so that all Nash equilibria are socially optimal. There's also always a reweighting of the players so that all Nash equilibria are socially optimal. And we can extend this to other things where players have different abilities or other kinds of things, which I won't get into. Just to spend one slide, and then I'll wrap up on what the kind of internals of this looks like. This is actually not a very hard game to think about once you sort of decide to think about it. Right, you build this bipartite graph of who could work on what. You add a supersync, and you discover it's actually a congestion game. a congestion game, think of as sort of highway congestion. You're trying to drive from your home to the destination, and you have to decide to drive through certain routes in the network. You thereby congest certain highways and pay something. Now, it's a congestion game here where you have a very strange payoff function. But still, using that general framework, we can sort of reason about the Nash equilibria that come out of this. Similarly, it sort of helps us interpret what's going on with these weird reweightings, right? The reweighting is really a tax that you're paying, right? You're paying a toll on certain problems because by default it would be overcongested. I have to offset that congestion, and what we do is charge a toll on that problem. Right? And that toll is essentially the unfairness that's driving people toward other things. And similarly, the Matthew effect in this model is some kind of a Stackelberg ordering on players, right? It says if players can move sequentially, right? Because in the extreme version of the Matthew effect, if the more famous person can get all the credit, then essentially the less famous person can move as though they know what's already happened with the higher, right? The higher player can move independently. And so there's also an orient. And so we can interpret various things going on here actually within this congestion game framework. I think there are a number of open questions here, and maybe part of my point is to sort of suggest what some of these are, right? So there are these sort of perverse, unfair things, right? That Bourdieu was, of course, right that intense competition does spread people out. The problem is it doesn't spread them out enough, right? There's still these hotspots, and you need to kind of help them spread out. And similarly, the reweighing player seems especially unfortunate that marginalization is sort of forcing people to embark on this risky course of action. Another interesting thing that goes on in the model, which I won't be able to get into, there's a community size effect. Take the same set of problems, but now increase the number of people, right? The equilibria actually look different. And in fact, as you increase the number of people, the credit on the harder problems tends to go up, right? Which makes sense, because with more people, you need to sort of have people fan out even more into these things. There are a whole bunch of open questions, right? Different levels, right? People could have different aptitudes on different projects. There's the issue of multiplexing of players' efforts, right? So collaboration is not part of this model, right? One could potentially explain things like when two people collaborate, why does one co-author get more credit than the other? Dependence among projects, right? Projects build on each other. You could imagine things where, although someone proved the hard lemma, the person got credit for proving the easy theorem that came after. Similarly, limited information dynamic arrival of projects, all of which could potentially build things in, including things like fads and transient versions of this. Okay, so I think there's a number of interesting things when you try to actually model what's going on, and thinking about the way in which evaluations aren't just happening and don't just have these weird properties, but they actually are creating incentives that feed back into the operation of the system. Okay, and then just to wrap up with one more slide, there's sort of this general question that's been sort of animating a lot of this, which is that really there are many situations where you see people expressing opinions, evaluations, valuing certain things higher than others. The harder problem is often to figure out why that's happening and sort of what the driving forces are behind them. And the hope here is that sort of these basic social science models, right, the theory of balance, theory of status, this theory of allocation of credit, can provide some kind of a vocabulary for looking at different situations and dissecting what are the forces at work. And arguably, there really are many forces happening all simultaneously creating these incentives. So I think overall, what's going on here is as we get this kind of data and as we think about other kinds of problems where these models might be relevant, there are a number of open questions that come up and a number of avenues for thinking about further directions. For now, I'll stop here. Thanks very much. Obviously, people have to leave. Madhu.
Yeah, so, in general, as a layperson, I feel that the advent of all these social networks, etc., seems to have led to a greater polarization of opinions. Is there anything in the theory that sort of supports?
Yeah, it's a good question. Right, so the question is, has the advent of online social media led to greater polarization of opinions? So there's a lot that's been written about this. And I would say, one does get that feeling. That feeling is also aided and abetted by media coverage, which essentially makes these points. I would say it's not entirely clear that one can trace sort of causally. One can say, okay, here it is, and here's how polarization is breaking out. But certainly there's been a lot of work. I mean, so one that's gotten a lot of attention is an argument, I guess really one of the first people to articulate was Cass Sunstein. And then more recently this book, The Filter Bubble, which a number of people may have read, which basically says, a long time ago, if you were a voracious consumer of political news media, there only was so much political news media produced in the world. right? It required a big capital expenditure to actually print newspapers and deliver them and distribute them. And so if you were a voracious consumer of stuff, you read a lot of stuff, and it was all over the political spectrum, and you inevitably bumped into stuff that disagreed with you, and you were forced to, let's look at that. Now, the sheer volume of what's out there means you can be a voracious consumer of political media and spend all of your time reading things that exactly agree with and reinforce your point of view. And that surely leads to a different kind of dynamics where now when two people from different sides go to discuss with each other, they don't even have some kind of common ground that they're starting from. They didn't both watch CBS News with Walter Cronkite or whatever it was that people did before. So that's certainly a style of argument people make. Now, one can push back on that, right? Because that's a plausibility argument that says this could be happening. There's the question of, do we have data that people are really not seeking out things? And in fact, when you look at people and when you talk to people who are big consumers of media, in fact, people often do try to seek out other points of view. And so it is more subtle than that, but that certainly is an argument that says the groundwork has been laid for this kind of polarization at a scale we haven't seen in the past.
Think about social good versus
Yeah.
side one. So the social good, we're creating it with what's good. The thing is, those are things there's a big tempo, so we don't know if all those are good.
Yeah.
How's that?
How's that come in? Yeah, no, so, and actually I mentioned the thing. Yeah, sorry, yeah. So what Shafi was asking was, there was this sort of abstract notion of there's the importance, it's a weight, and we all know it. But of course, real importance has a temporal component. We don't know what will be important, and so something could look unimportant, and later it actually becomes important. Yeah, and actually I sort of was hoping to hint at that with the last two, dependence among projects and dynamic arrival of projects. So new things arrive, and you discover that something you solved actually becomes useful for future things. Creates a much more complicated situation. In a way, you could argue for proving if this is sort of a negative result, making simple assumptions makes the negative result stronger. I guess all it's saying is that even if everyone completely agreed on what was important, even then there would be this societal benefit from unfairness. But you could argue that uncertainty actually may mitigate the unfairness. The fact that we don't know what's going to be important actually might end up. So it's a very good question. Suppose things had uncertain value, would that actually maybe offset some of the unfairness? That's one thing. And of course, implicit, I guess, also is that I chose to measure social welfare as the expected value of what got solved. If you believe there's also a social welfare component of people don't have the perception that their research community is unfair to people, that would also, be some other component, which is not being modeled here. But yeah, no, I think it'd be a very interesting question if uncertainty about the weight actually offsets some of the unfairness would be a fascinating question. Yeah, of course.
Since you make, like, last thing, might make some kind of two qualitative prediction. One is that really committees would tend to give more credit to difficult work even of the same importance. And the second thing is that famous researchers would tend to work on easier problems. Do you see it?
So do we see evidence of that, or you mean do we see that as being the qualitative? Well, so right. So those are some qualitative predictions. I guess the prediction for the Matthew effect would be that famous researchers would behave as though there's limited other competition, right? So if that would cause them to work on easier problems, if they're important, not if they're not important, right? Things of higher, but it would say that famous people operate as though there's less competition because they're going to experience less competition in the event of a collision, right? Whereas less famous people have to be more aware of who they're going to collide with in this situation. Yeah, the argument about easier, so under some simple, you can sort of create simple families of instances where you see that, yes, indeed, it monotonically follows disordering. Other ones, because the weight allocation is some kind of complicated assignment problem, it's hard to make sort of completely simple statements. But that, in simply parameterized families of instances, as I said, one sees some of this tendency toward the harder problems are getting more weight. Yeah.
Reasons to believe the sort of reassignment of weight is kind of anthropological or leads towards social optionality? I mean, maybe we do the reverse. Maybe we decrease social optionality. Or I mean, what incentivizes this free weight?
Yeah. Well, so the question of what so there's no evidence. I mean, so this is sort of, as I said, kind of a proposal for a starting point for a lens through which to look at what's going on. It's a very interesting question to say, are the right problems being solved? How would you even quantify that? Because just because some reweightings make things better, obviously other reweightings make things worse. It's hard to say. What's the incentive to create this reweighting? That I would argue there is, right? So when program committees or funding agencies panels get together, they actually are trying to make their community look good to the rest of the world, right? They really are committees that meet to articulate strategic priorities for a research area to say, we aren't getting enough respect at NSF, DARPA, the media, other fields of our other subdisciplines, name it, you name it. And because of that, we're going to have to figure out how to prioritize what we're working on. So one does actually, and that's the point I made about there being a planned economy here. There really are committees that get to it. Now, how successful they are is not clear, but they certainly have an impact on people. Yeah.
So how would you identify rogue academics who are consciously exploiting these dynamics?
It's a question of what it means to consciously exploit it. I mean, all this is saying is...
You need to be a rogue. Well, a lot of this discussion seemed implicit, that this is a model, but people don't sit down and compute these weights.
They don't compute weights.
Decisions, right?
But it is true that people do think about, should I work on this or should I work on that? And the argument, and this is not argument, this is all the literature I was drawing on in sociology of science. The argument says that when people say, should I work on this or should I work on that, they are thinking about which is going, what are going to be the career consequences for me of working on this versus that. So I wouldn't say those are rogue academics, those are just people thinking about, so researchers are driven both by the credit they're going to receive as well as the scientific beauty of the questions that it's
Decisions are generally optimal, or do you think there are arbitrage possibilities?
Again, I'm not quite following off, but happy to take this offline. But yeah, I'm not quite sure what arbitrage means. Yeah.
So we now have this huge data set for this Milgram minimal paths between people on Facebook. Is there evidence that, or are people any good at actually finding these paths when presented with this task? Are people good at finding a set of random connections down the road to people far away?
That's good. I guess the argument of the Milgram experiment that you would draw from that is people are at least pretty good, because 6 in the end is a small number, right? So no matter how low the optimum is, 6 is by any measure small. It could have been much, much huger.
But also, are we getting better at it over time as the world becomes more interconnected?
Yeah, well, so this argument with the exponent says we could be getting better or we could be getting worse, right? So if you consider the extreme limit where people just bump into each other randomly on the internet and make friends, suddenly trying to find someone in Boston may actually become more difficult. Because, you send a letter to Boston and suddenly discover no one in Boston knows each other because they're all on the internet making friends with people in California, right? So it isn't clear that a more connected world actually makes this experiment easier. It actually says that the optimum is an interior optimum, where you need the right distribution of links, including links right. Now, of course, in the end, you may use some other axis along which to route the message, right? It could just be that geography evaporates and is replaced by something else. But all of these are interesting questions about the... But yeah, as to how good people are, there have been some attempts at, how close do they come to the optimum? At measuring this, some papers by Kilworth and Bernard, for example, looked at this question. Clearly, people are, it's not surprising, not finding the shortest path, because there really are these chance oddball connections that your next door neighbor really did know someone who could have gotten you much closer and you just didn't know this. But I guess the point has tended to be not about relative performance, but about just absolute performance, that even with complete decentralization, 6 is in the end a small number. And that the other issue here is replicability. Part of the miracle of the Milgram experiment was that so many people actually participated, right? You get a letter in the mail from a stranger saying, I'm running an experiment, please mail this to your friends. 3/4 of people participating says something about the kind of people he mailed it to, the era in which this experiment was performed, the general trust level society had for scientists, and so forth. Recent attempts at replicating, saying, please sign on to this website and help me do this experiment, much lower replication rate. So it's been a hard experiment to replicate, not because people are getting worse, but because people just don't do it, right? Yeah.
There's a story you're telling here about game theory, but it's missing the story about the networks. And I wonder that there's a comment raised about making the problem easier to solve, and I think that you dismiss that, but I think that there's theories about sort of creativity that suggests people occupy brokerage roles between communities.
Oh, yeah, brokerage, yeah.
You sort of be able to make the problem easier, you have more perspectives on it, or there's sort of the Linus principle that if you have enough eyes, all bunch of shallows. There's sort of structural sorts of arguments you can make that say if you kind of change the configuration of people working on the problem, that you can make it easier potentially.
Yeah, no, and again, just to start with a superficial answer to your question, absolutely that multiplexing of people is a good extension of all. And I guess I would change the difficulty. I guess I would argue that's changing the difficulty through a feature of the model, not just by change. As in, the community can't sit down and decide, we have decided, which was my answer to that. The community can't sit down and say, we've decided to make this probability change from 1/2 to 4/5, but they can decide we would allocate more people to it, right? That effectively changes the probability, which is actually what's happening in this model, right? If more people work on the problem, it really did get easier, because now its success probability is this, which has changed. Brokerage is an interesting point, right? Because that's not just sheer numbers. Sheer numbers achieves this. But yeah, there's a whole separate issue here about people seeking out status. Should they look for embedded ties or bridging ties, right? And depending on the context you're in, Structural holes type arguments certainly say that brokers can be effective. What would that mean here? It's an interesting question, right? But it would presumably involve an interaction of several communities, right? Because one tends to think of structural holes as creativity amplifiers, right? You are the unique person who can combine ideas from here and from there, and that enables you to solve problems that couldn't be solved. If I wanted to build that into the model, I would somehow need multiple communities probably that meet at juncture points, and if you occupy those juncture points, it gives you some leverage. And that'd be very interesting to look at. Yeah, Bob.
Failures, probabilities, or independence is very dubious.
Yeah, you mean that everyone has their independent chance? Yeah, I agree. It'd be hard, because these are people with similar background theory, they're all going to succeed. Yeah, it's a good question. And you could ask what would happen if that changes. That would make this much more steeply concave, which would say you want even fewer people. I mean, in some sense, I'm calculating in real time, but the worry is that would actually make this effect even worse, the unfairness effect, because you would want even fewer people on the easy important problem, because multiple attempts are going to sort of be correlated. But
You might also think people are ordered somehow by their ability. That would have
yeah, so there is an extension somewhere in here that you can have players of ability, and in some sense, and that actually sort of works like that changes how you want it. And actually, the Matthew effect, to operate optimally, socially optimally, the Matthew effect has to take ability into account and weigh things. And of course, it isn't clear the real Matthew effect does. Should we take further questions offline? Sounds great. Okay, thanks again.